Welcome to RadOnc Smart Review Physics Edition. Today we're diving into something really fundamental in radiation oncology physics. What actually happens when those high-energy photon beams we generate, hit the patient?
That's right. We've talked about making the beams, but now we need to get into how they interact, how they actually transfer their energy, and how that leads us to concepts like Kerma and Absorbed Dose. This stuff is crucial, really, for everything from dose calculation algorithms to understanding imaging contrast and even designing shielding.
Okay, let's unpack this. First off, a really key distinction. We've mentioned charged particles before, like electrons and protons,
Mm.
and how they cause direct ionization. They just barge through, messing with atoms directly. But photons are X-rays and gamma rays. They're different.
Exactly. Photons have no charge, right? So they don't cause that continuous trail of ionization as they move. They are what we call indirectly ionizing. What's fascinating here is they can travel quite a way, then suddenly have a significant interaction.
And in that interaction,
They transfer energy to a charged particle, usually an electron. And that electron then races off and causes the ionization and excitation in the surrounding tissue. So the photon sort of starts the process, but it's the secondary particle that does the bulk of the local work.
and as these interactions happen, photons get taken out of the original beam. Some get absorbed completely, some just get scattered in a different direction. This whole removal process is called attenuation.
Right. And for a nice simple beam where all the photons have the same energy, a monoenergetic beam, this attenuation follows a really predictable pattern. It's exponential. Think of it like radioactive decay, but instead of time, we're looking at thickness of material.
Ah, okay, so there's an equation for that.
Yep. The number of photons you have left, let's call it n, at thickness x, or nx, is related to the number you started with, n0. By nx equals n0 times raised to the power of minus mu times x.
Okay, N0 is the initial number, X is the thickness of the material. And that Greek letter, mu, what's that?
That's the linear attenuation coefficient, mu. It basically represents a fraction of photons that get removed from the beam per unit thickness. So its units are often like per centimeter or millimeter inverse.
And its value depends on.
Oh, it depends heavily on the photon energy and also on the material itself, specifically its density, which we often write as rho, and its atomic number z.
We've got some pretty useful rules of thumb for water or tissue, which is what we mostly care about clinically. Like for 6 MV photons, attenuation is about 3% per centimeter.
Roughly, yeah. And for 15 MV photons, it drops to about 2% per centimeter. And in something much less dense, like lung tissue, it attenuates way less, maybe only a third or a quarter of what water does, because mu depends directly on density.
Okay, so since that linear coefficient mu is density dependent, we often use something else.
Exactly. We often use the mass attenuation coefficient. That's simply mu divided by the density, rho. By dividing out the density, you get a value that's more characteristic of the material itself, regardless of whether it's solid, liquid, or gas.
Ah, that makes sense. So it's interactions per gram, maybe.
Pretty much. The units are typically centimeters squared per gram. It tells you about the probability of interaction per unit mass, which is often more fundamental when comparing different materials or tissues.
All right, so attenuation tells us photons are disappearing from the beam. But in radiation therapy, we don't just want them gone, we need them to deposit energy to kill cancer cells. How do we track that energy deposition?
That's the crucial next step. This raises an important question. We need to know how much energy is actually being handed over. For this, we use the energy transfer coefficient, written as mos sub Tr. This accounts for the average energy that gets transferred from the photons to the kinetic energy of those charged particles, those secondary electrons, right at the interaction site.
But hang on, those fast electrons, they don't necessarily dump all their energy right there at that exact spot, do they? They travel a bit.
They certainly do. And sometimes, especially if they're high-energy electrons moving through high-Z materials, they can lose some of that kinetic energy by radiating it away as Bremsstrahlung photons. Brem photons.
Ah, the braking radiation.
Exactly. And those Brem photons can travel quite far, potentially escaping the local area we're interested in. So to account for just the energy that gets deposited locally through ionization and excitation by those electrons, we use the energy absorption coefficient mu sub En.
Okay, so mu sub En focuses just on the locally deposited energy. That means mu sub En must be less than or maybe equal to mu sub Tr.
Always. The relationship is mu sub En equals mu sub Tr times the quantity, 1 minus g. That G factor is simply the fraction of the initial kinetic energy given to the secondary electrons that gets re-radiated away as Bremsstrahlung.
And G would increase with?
G increases with the electron's energy and with the atomic number Z of the material they're traveling through. More energy, more chance to radiate. Higher Z, stronger braking field.
Okay. And the mass energy absorption coefficient mu sub En divided by rho, that's the one most relevant for calculating the actual dose deposited.
Precisely. That quantity tells us the energy deposited locally per unit mass. And this leads us directly to two absolutely vital concepts: Kerma and absorbed dose.
Kerma, Kerma. That stands for kinetic energy released per unit mass, right?
Correct. It's formally defined as the sum of the initial kinetic energies of all the charged particles set in motion by uncharged particles, like our photons, within a little volume element divided by the mass of that volume.
Units are joules per kilogram, same as gray.
Same units, joules per kilogram, which we call the gray. And Kerma itself can be split. Total Kerma, K, is divided into collision Kerma, K sub col, and radiative Kerma, K sub rad. Collision Kerma is the part transferred to electrons that they then lose through collisions, ionization, and excitation. That's the part we care about for biological effects.
And collision Kerma is related to that G factor again.
Yep. Collision Kerma, K sub col, equals total Kerma K times 1 minus G. It's the locally deposited fraction. Radiative Kerma is the part lost as Brem.
Okay, so Kerma is fundamentally about the energy transferred to the electrons at the point of interaction. Absorbed dose, D, is about the energy that's actually absorbed locally from those electrons as they slow down and travel through the tissue.
That's the critical distinction. Think about a megavoltage photon beam entering a patient. Right at the surface, the number of photons hitting is highest, so the photon fluence is maximum. Therefore, Kerma is maximum right at the surface.
But the absorbed dose isn't maximum there.
No, it's actually quite low. Those electrons that get knocked loose are mostly traveling forward deeper into the tissue. They haven't had the distance yet to deposit much of their energy right there in that superficial layer. This difference is the physical basis for the skin-sparing effect we value so much in MV therapy.
Okay. So as the beam goes deeper,
As the beam penetrates, two things happen. Kerma starts to decrease because the photons are being attenuated, but the electrons set in motion near the surface are now reaching deeper depths and depositing their energy, plus new electrons are being generated deeper down. So the absorbed dose actually builds up with depth.
until it reaches a peak, Dmax.
Exactly. Absorbed dose peaks at the depth of maximum dose, Dmax. The depth of Dmax depends on the beam energy. Higher energy beams have longer range electrons, so Dmax is deeper.
And beyond Dmax?
Beyond Dmax, the absorbed dose starts to decrease as well, mainly because the Kerma, the production of new electrons, is falling off due to photon attenuation. The dose curve roughly parallels the Kerma curve beyond Dmax, but it's shifted deeper because of the forward range of those electrons.
And it's in this region, beyond Dmax, that we approach something called transient electronic equilibrium.
That's the term. It means that for any small volume, the number of electrons carrying energy into that volume is roughly balanced by the number carrying energy out, plus the energy that's actually deposited within the volume by electrons slowing down.
So dose and Kerma are related there.
In this region, under transient electronic equilibrium, the absorbed dose, D, becomes proportional to the collision Kerma, K subcol. If you had perfect electronic equilibrium, where electrons stopped exactly where they were created, dose would equal collision Kerma. But for MV beams, it's usually transient equilibrium.
Okay, so the key takeaway here, Kerma is highest at the surface, always decreasing with depth. Absorbed dose starts low, builds up to Dmax, then decreases. And crucially, before Dmax, Kerma is greater than absorbed dose.
You got it. That relationship is fundamental.
So now we know about energy transfer and dose, but how do the photons actually interact to kick off this whole process? You mentioned 5 main ways.
Right. Let's get into the mechanisms. There are 5 main interaction processes photons can undergo. First, at very, very low energies, there's Rayleigh scattering, sometimes called coherent scattering.
Okay, what's that?
It's pretty simple, actually. The photon interacts with the whole atom, makes the electron cloud kind of wiggle for a moment, and then the atom re-emits a photon with the exact same energy, just going off in a different direction.
So no energy is actually deposited?
Nope. No energy loss, no ionization. It just changes direction. It's really only significant at very low energies and doesn't play much role in therapy or even diagnostic imaging, frankly. Pretty negligible for us.
Okay, negligible. What's next, and more important, especially at lower, diagnostic energies?
That would be the photoelectric effect. This one is dominant at the lower end of the kilovoltage range. Think typical diagnostic X-ray energies.
And how does this one work?
This is a true absorption event. The incoming photon hits a tightly bound inner shell electron, often from the K or L shell. The photon completely disappears, vanishes.
And all its energy goes where?
All of its energy is transferred to that electron, minus the energy that was holding the electron in its shell, its binding energy. That electron gets ejected from the atom with kinetic energy. We call it a photoelectron.
Okay, and the probability of this happening, I remember you said it depends strongly on Z and energy.
Very, very strongly. This is critical. The probability shoots up rapidly with the atomic number of the atom, roughly is Z cubed. So high Z materials are much more likely to have photoelectric interactions.
Z cubed, wow.
Yeah, huge dependence. And it drops off just as dramatically as the photon energy increases, roughly as 1 over E cubed. Also, the photon has to have enough energy to kick the electron out, more than its binding energy. This leads to sharp jumps in attenuation called absorption edges.
What happens in the atom after the electron is gone?
You've got a vacancy, an empty spot in an inner electron shell. An electron from a higher outer shell will quickly drop down to fill that hole. When it does, it releases energy either as a characteristic X-ray photon specific to that element or by kicking out another electron, which we call an auger electron.
And the energetic photoelectron itself?
That photoelectron, plus any characteristic X-rays or auger electrons produced, deposits its energy very locally right near the site of the original interaction.
Relevance. You mentioned diagnostic X-rays.
Absolutely dominant for diagnostic X-rays, typically in the 20 to 100 keV range.
Yeah.
And that Z-cube dependence is why we get such great contrast between bone, which has a high effective Z, and soft tissue, which has a low Z, on our X-ray images. It's all photoelectric effect.
Okay, super important for imaging. Now, moving up in energy
Mm-hmm.
into the therapy range, what takes over?
Now we get to the king of therapeutic interactions, Compton scattering.
Yeah.
This is the dominant process from around, say, 30 key all the way up to maybe 25 or 30 MeV.
Oh, what happens in Compton scattering?
Here, the incoming photon interacts with a loosely bound outer shell electron. These electrons are bound so loosely compared to the photon's energy that we can basically treat them as free electrons just sitting there at rest.
Okay, so it hits a free electron.
Right. The photon transfers some of its energy to this electron, knocking it out of the atom. This ejected electron is called a Compton electron, or sometimes a recoil electron. The photon itself doesn't disappear, but it loses energy and scatters off in a different direction.
So unlike photoelectric, the photon survives, just with less energy.
Exactly. Energy and momentum are conserved in the whole interaction, distributed between the scattered photon and the Compton electron.
Now, the probability dependence here is key and very different from photoelectric, right?
Hugely different, and this is a massive point for therapy. Yes. The probability of Compton scattering does decrease as photon energy increases, but much more slowly than photoelectric, roughly as 1 over E.
Okay, 1 over E. But the dependence on Z.
This is the kicker.
Yeah.
It's almost independent of the atomic number Z. Per gram of material, bone and soft tissue, attenuate photons almost identically via the Compton effect.
Wait, really? So why does bone look different on an MV port film then? Just density.
Mostly density, yeah. Compton does depend on the electron density, the number of electrons available per gram of material. Most materials, like water, soft tissue, even bone, have very similar numbers of electrons per gram. The exception is hydrogen.
Hydrogen. Why?
Hydrogen has no neutrons, just a proton and an electron. So for its mass, it has roughly double the number of electrons per gram compared to most other elements found in tissue. Fat has more hydrogen, so slightly higher electron density. But overall, the Z dependence is minimal compared to photoelectric.
Interesting. And the energy sharing depends on the angle.
It does. The photon just has a glancing collision, it scatters at a small angle and loses very little energy. If it scatters at 90 degrees, its energy drops towards 0.511 MeV.
The electron rest mass energy.
Exactly. And if it scatters straight back, 180 degrees, the photon energy gets even lower, approaching 0.255 MeV, or half the electron rest mass energy.
And the electron, where does it go?
To conserve momentum, the Compton electron always gets ejected in a generally forward direction relative to the incoming photon.
Okay, relevance clinically. This is our main dose mechanism.
This is absolutely how our therapeutic megavoltage photon beams deposit the vast majority of their dose in soft tissue. Those Compton electrons are the primary agents causing ionization and excitation within the tumor volume. It's also, unfortunately, a major source of scattered radiation that fogs up our images, both diagnostic and MV ports.
Got it. Compton is king for therapy dose. What happens if we go even higher in energy, like above 10 or 20 MeV?
Then we start to see pair production become significant. This interaction has a definite energy threshold. The incoming photon must have at least 1.02 MeV of energy,
Why that specific number?
because that's exactly twice the rest mass energy of an electron, 0.511 MeV. In pair reduction, a high-energy photon passes close to the strong electric field of an atomic nucleus.
The nucleus itself.
Yes, the field of the nucleus. And the photon's energy spontaneously converts into mass. Specifically, it creates a pair of particles, an electron and its antiparticle, a positron.
Wow, matter creation.
Pretty much. EMC squared in action. Any energy the photon had above the 1.022 MeV threshold is shared between the electron and positron as kinetic energy, making them fly off.
And the probability of this happening.
It increases with photon energy once you're above the threshold, and importantly, it increases significantly with the atomic number of the nucleus involved, roughly a Z squared. So high Z materials are much more prone to pair production.
Z squared this time. Okay. What happens to that positron? It's antimatter.
It is. It travels a short distance, losing its kinetic energy like an electron does. But once it slows down enough, it inevitably encounters an electron. Matter meets antimatter.
Annihilation.
Annihilation. They both disappear, and their combined rest mass energy is converted back into pure energy, specifically two 0.511 MeV photons that fly off in opposite directions 180 degrees apart to conserve momentum.
And those 2.511 MeV photons. That's the basis for PT imaging, right? Detecting those pairs.
Exactly. That annihilation radiation is what PT scanners detect. There's also a related process called triplet production, where the interaction happens near an orbital electron instead of the nucleus. It has a higher threshold, 2.044 MeV, and is less common.
So relevance of pair production in therapy.
It becomes an important contributor to attenuation and dose deposition for beams with energies significantly above, say, 10 MeV. It starts to compete with, and eventually overtake, Compton's scattering at very high energies, especially in high Z materials like shielding. It's why higher energy beams can sometimes have slightly better penetration, but it also complicates things.
Okay, one more interaction to cover.
The last one, generally requiring the highest energies, is photodisintegration.
Photo disintegration. Sounds dramatic.
It is. Here, a very high-energy photon doesn't just interact with the electrons of the nucleus's field. It gets absorbed directly by the nucleus itself.
Into the nucleus.
Yep. This dumps a lot of energy into the nucleus, making it highly unstable. To get back to a more stable state, the nucleus immediately ejects a particle, most commonly a neutron, but sometimes a proton or even an alpha particle.
What kind of energy does this take?
The threshold energy depends on the specific nucleus, but for the materials typically found in a linear accelerator treatment head, like tungsten in the target or lead tungsten in the collimators, the threshold is usually around 8 to 10 mega electron volts.
8 to 10 MeV. That sounds familiar.
It should. This is the primary reason why we get unwanted neutron contamination from LINACs operating above about 10 MeV. Those high-energy photons from the beam hit the high Z components in the head.
And knock neutrons out, photoneutrons.
Exactly, photoneutrons. This is a really big deal for radiation protection. Neutrons are hard to shield, require special door designs with materials like polyethylene or concrete, and they contribute an unwanted whole-body dose to the patient, which has implications for secondary cancer risk.
Wow, okay. So operating above 10 MeV really changes the game regarding shielding and safety because of photodisintegration.
It really does. It's a major consideration.
So let's pull this all together. We've got these 5 interactions, each dominant in different energy ranges and depending differently on Z. How does knowing all this actually influence our clinical decisions?
Well, it dictates our imaging choices. For starters, we use kilovoltage beams for diagnostic CTs and X-rays because we want that Z-cubed dependence of the photoelectric effect to give a sharp contrast between bone and soft tissue.
And conversely, MV portal images look washed out.
Because they're formed mainly by Compton scattering, which barely cares about Z, the little contrast you see is mostly due to differences in density and thickness.
Makes sense. And for planning therapy.
Knowing Compton is dominant for our typical MV beams in tissue simplifies dose calculation in a way. We don't need super complex corrections for the Z of bone versus tissue like we would with KV beams. The main thing we need to account for accurately is the difference in electron density, which is closely related to physical density.
So density corrections are paramount for MV planning systems.
Absolutely. And the choice of beam energy itself involves these trade-offs. Going to higher MV, say 15 or 18 MV, might give slightly deeper penetration, partly due to the onset of pair production, which can be good for deep tumors.
Ah,
But you cross that photodisintegration threshold around 10 MV, introducing neutrons. So you need much more shielding in the room, heavier doors, maybe a maze, and you have that extra patient dose component to consider.
Yeah.
It's a balance. 6 MV is often a sweet spot, good skin sparing, decent penetration, no neutrons.
and shielding design itself must be tailored to the dominant interaction, right?
Totally. For a diagnostic X-ray room, low energy kV, lead is fantastic. Its high Z maximizes the photoelectric effect, efficiently absorbing those photons. But for a high-energy LINAC vault,
Lead isn't enough.
well, for the primary beam, you need shear mass to handle Compton scattering, so thick concrete is the main barrier. Lead might be used strategically, but concrete provides the bulk. And if you're above 10 MV, you also need neutron shielding. That's where the hydrogen in concrete helps. Or adding layers of polyethylene inside the door comes in. You have to stop photons and neutrons.
It all comes back to the physics of these interactions. Okay, let's crystallize some of this. Time for some clinical pearls, the absolute must-remember points for boards and practice.
All right, Pearl 1, photoelectric effect. Think kilovoltage energies. Think Z-cube dependence. Think inverse E-cube dependence. Think imaging contrast.
Pearl 2, Compton scattering. Think megavoltage therapy energies. Think largely independent of Z. Think dependent on electron densities. Think roughly 1 over E dependence. Think dose deposition in tissue.
Pearl 3, pair production. Think threshold energy, greater than 1.022 MV. Becomes important at high MV, especially above 1015 MV. Probability increases with energy and with Z squared. Think high energy, high Z.
Pearl 4, photodisintegration. Think threshold energy around 8 to 10 MeV. Think neutron contamination in LINACs operating above 10 MeV. Think shielding implications and patient safety.
And don't forget that rough 50-50 rule for water. Photoelectric and Compton crossover around 30 keV. Compton and pair production crossover somewhere around 24 to 30 MeV. Gives you a quick sanity check for which process dominates.
Excellent pearls. Ready for a quick board blitz? Let's test these concepts. Question 1. Which photon interaction process is most responsible for the difference in image contrast between bone and soft tissue on a diagnostic kilovoltage X-ray?
Okay, diagnostic kV. Contrast between bone, high Z, and tissue, low Z. That's got to be the photoelectric effect because of its Z-cube dependence.
Correct. Explanation. The probability of the photoelectric effect is roughly proportional to Z cubed. Bone's higher Z causes much greater attenuation of kV photons via this effect, creating contrast. Question 2. A 10 mega electron volt photon beam is incident on a lead shield. Lead has ZeL 82. Which photon interaction process is likely dominant within the lead at this energy?
10 MeV is getting up there, and lead is high Z. Compton dominates in water up to maybe 25 MeV, but pair production increases with Z squared. So in high Z lead, pair production probably takes over much earlier. I'll say pair production.
You got it. Explanation. Pair production's Z-squared dependence makes it dominant over Compton at lower energies in high Z materials compared to low Z materials. By 10 MeV in lead, pair production is likely dominant. Question 3. Compton's scattering probability is primarily dependent on A, atomic number Z, B, mass number A, C, electron density, electrons per gram, D, photon energy only.
Compton. You said it's almost Z independent, but depends on how many electrons are available to hit. So C, electron density.
Perfect. Explanation. Compton probability is largely independent of Z, but directly proportional to the number of electrons per unit mass. Question 4. Neutron contamination becomes a significant concern for linear accelerators operating above what approximate photon energy? A, 1 MeV, B, 6 MeV, C, 10 MeV, D, 25 MeV.
That's the photodisintegration threshold we talked about. Around 8 to 10 MeV is where it starts to matter in LINAC material. So C, 10 MeV.
Excellent explanation. Photodisintegration, creating photoneutrons, generally has a threshold around 810 MeV in relevant LINAC materials like the target and collimators. Okay, so let's quickly summarize what we covered today. We established that photons are indirectly ionizing. They interact via processes that remove them from the beam attenuation, which follows that exponential equation.
And we made that key distinction between Kerma, the kinetic energy released to electrons, and absorbed dose, the energy actually deposited locally. That explained the dose buildup effect, Dmax, and the concept of electronic equilibrium.
Then we walked through the 5 key interactions: the almost negligible Rayleigh scattering, the photoelectric effect, dominant at kV energies with its strong Z-cube dependence crucial for imaging, Compton scattering, dominant at therapy MV energies depending on electron density and responsible for dose in tissue, Pair production, needing over 1.022 MeV and depending on z-squared, important at high energies. And finally, photodisintegration, kicking in above 810 MeV and causing neutron contamination.
And understanding how these interactions compete and dominate based on photon energy and the Z of the material, well, it really does underpin just about everything, doesn't it? From why our images have contrast, to how TPS algorithms calculate dose, to how we safely design treatment faults.
It really does. Thinking about how these microscopic events, these individual photon interactions, add up to create the macroscopic dose distributions we shape and deliver to patients. It's pretty incredible when you step back and think about it. A real reminder of the fundamental physics driving our clinical practice.
Absolutely. And building right on this, next time we'll get into how we actually go about measuring that absorbed dose accurately in the clinic. We'll talk about different types of detectors and the theories behind them, like Bragg-Ray cavity theory.
Sounds great. Remember, you can find complete practice oral boards over at radonsmartlearn.com. Be sure to subscribe to RadOnc Smart Review for our next session. Thanks for tuning in.